Hello, welcome back everyone to this video on YouTube. So in the last video we were talking about some boundary conditions. I went through a few of them, especially with the external wall heat flux temperature, flow rate, inlet velocity. I kind of barely touched that, and of course there's an inlet outlet as well. Now just before I continue, I just want to clarify before I go on, what is inlet outlet condition? Inlet outlet condition is basically inlet outlet. I guess CFD support is good. This is one of the first things you will find on Google. So basically, it will apply a zero gradient. Okay, you can see here the inlet outlet boundary condition is not only the same as zero gradient, but in the case of reverse flow, you don't apply the zero gradient boundary condition anymore. You will apply a fixed value. So you see, for example, in the inlet here, you will usually have a fixed value where fluid is flowing into this domain. Okay, it will flow into this domain, and it will have an inlet. You will have a fixed value, and then when you exit the domain, you have a zero gradient boundary condition. But sometimes, especially in the case of turbulence, you will have a what do you call that? You will have a sort of sometimes a reverse flow, or sometimes there's a flow instability. You can still have a reverse flow. Then OpenFoam will be wondering, what value you should have when it comes back into this domain. Oh wow. Okay, great. Yes. Never mind. What value will it have when it comes back into this domain? And you can specify that value. If you left it to zero gradient, it may result in some instabilities there, numerical instabilities, and that's usually not good. So sometimes the inlet outlet boundary condition is used to improve the stability of the case, especially when it comes to this what do you call that, reverse flow. Okay, so it's very relevant in terms of turbulent cases, especially when you have LES, large eddy simulation kind of a case going on here. Now this is done for the shell part, and the part for the tube is also pretty similar. Okay, FE schemes, FE solution, and decomposed parallel dictionary will be more or less the same, and change dictionary will be very similar in terms of entries, just that the boundaries you have are different. Okay, the boundaries you have will be different, and again, if you forget which boundaries to use, you can go to VI tube and you go to polymesh boundary. Okay, so you'll see there are there are only three boundaries here. One is tube N1, one is tube N2, and one is tube to copper. So it's basically a pipe flow. Alright, so over here you'll see the velocity. Over here I give the tube N number 2 a flow rate inlet velocity. Okay, so if I want a counter current flow heat exchanger, I will make tube N2 to be the inlet, and then the outlet will be a zero gradient, which I designate tube N1. Likewise, for temperature, I assign a fixed value. The temperature of the fluid coming in will be a uniform 500 Kelvin, so it will be a hot. The tube side will be hot and the shell side will be cold. Epsilon will be again similar to before we have calculated. Otherwise, it will be a wall function. Okay, so I doing this wildcard here, using this wildcard, the dot star thingy you see on top, this is called wildcard. And what this does actually, it will make every single patch into this epsilon wall function. Then when I designate tube N1 and 2 to be calculated an internal field, it will change the boundary condition from epsilon wall function into the calculated, and the value from 0.01 into internal field, which is again 0.01, as you see here. It's not uniform 0.01 on its own. Now for K, same thing, same idea here. I assign wall boundary conditions, then I assign inlet outlet to the outlet end. Okay, inlet outlet to the outlet end, and then of course the turbulent kinetic energy inlet to the inlet end. Again, I just left it around 0.05, and you can estimate using the Reynolds number if you want to be a bit more vigorous about it. I left the links here. Okay, so heat RGH is similar to what I discussed in the last video. Pressure as well. Pressure is mostly calculated. Then you have the rho. I again explained in the last video. Omega also, again as explained in the last video, I assigned this turbulent mixing frequency inlet to the inlet of this tube, and the tube end will be inlet outlet boundary condition. Alpha will have a compressible alpha wall function there with a turbulent Prandtl number of 0.85 at the first cell of the wall. So this is for first cell of the wall. Alright, so tube N1 and 2 will be here. And nu T, again, same concepts to apply over here. And that should basically do it for all your OpenFoam stuff, your OpenFoam directories. So now what you have is this Oran serial pre. Okay, I've actually scripted in the code into this Oran serial pre. So what will I do? I will use this bash terminal or bash terminal emulator for this command line interface language for the shell, so to speak. The all clean script is run. Then I use ideas UMV to foam. Of course, I can have a poly dual mesh, which will change this tetrahedral mesh into polyhedral. But if you want to get poly dual mesh to work properly in CHT multi-region foam, it is a very, very big hassle. I've not fully figured out at the moment of creating this video. I have not fully figured out how to do it yet, because poly dual mesh actually does not work very well with CHT multi-region foam, because you don't poly dual mesh does not preserve the cell zones. Okay, I will show you what I mean if I have the time. But first, I do this ideas UMV to foam. I do the transform points, restore zero directory, and then I split the mesh regions. Now, of course, I do the usual CHT multi-region foam things, including change dictionary for each region. Then I do this touch CHT pipe heat exchanger.foam. All of this should take pretty short while. So just ignore the poly dual mesh for now, and we'll just focus on doing it with a tetrahedral mesh. So executing this, I will be able to run all of this code, and this is what you will have here. Okay, this is what you will have here. Alright, and if you run CHT multi-region foam now, your mesh should be ready for calculation. Unfortunately, the case that you see here, while CHT multi-region foam will run, it is not numerically stable just yet. Okay, so I set the maximum diffusion number at about 1000 because the mesh size is not very optimal, so this diffusion number is huge. But otherwise, the copper should be at a more or less constant temperature for the whole thing. It behaves like a lump capacitance kind of a thing. Okay, more importantly is the fluid region. So what happened to the fluid region? Okay, is the mesh too coarse or too thin? We'll have to see. Okay, let's see. Pipe heat exchanger Salome, and this is what we have. Now let's take a look at the mesh, and we look at the surface with edges. Now if you take a look at the shell side, now basically only two layers of tetrahedrons to work with. So you have this layer which is just next to the wall, and this other layer which is also just next to the wall. Now what happens over here is that wall functions will be applied to this set of cells, the first set of cells adjacent to the wall, and this other set of cells adjacent to the wall. So what will happen is that this fluid region won't be very well resolved. In fact, if you try to apply wall functions like so, you might have this numerical instability error, because the first cell of the wall will have the values dictated by the wall functions and not by the Navier-Stokes equations, and therefore I think the whole solver will actually just crash, as what you see here. So one possible remedy to this situation is actually to use a finer mesh, which I have just prepared over here. Now hopefully you can see the shell side. If I just only do the shell side, okay, if I only just do the shell side, let's see, group of volume, okay. If you look at the shell side, at least there are about 5 layers now of cells, or 4 to 5 layers depending on where you look. There should be about 4 to 5 layers of cells where you can have fluid flowing. So at least this won't have just 2 layers and then you have some kind of funny issue. So at least you have this going for you. Now of course in the inlet and the outlet, there will be a lot of cells there. You have a lot of cells over here, in fact too many cells. So that's perhaps one potential issue. And if you want to do a quick calculation, that could be a potential issue. If you look at the tube, side, you will have a lot of cells there. That means this region is probably a little over resolved. I don't want to find a mesh because it will take very long. So this for this case, I actually use you can evaluate the mesh. You'll see there are about 600,000 cells here. So this case is going to take quite a while to run, because you don't generally want to go over 100,000 cells if you want your case to go very fast. So this is what you kind of have to deal with if you make your mesh very fine. But hopefully this means that the mesh will be more stable. And what algorithms did I use? Let's see. Yeah, these are the algorithms I use. I use a custom fineness with growth rate of 0.2, number of segments per edge to be 3, number of segments per radius to be 10. So that's a lot of meshing to do. Okay, so this is how I do it. I didn't use the second order thing. I use this optimize. I check this optimize box, and this netgen will be able to oopsie. This netgen should be able to just get this thing running. Okay. Compute. So it will take a while to compute. And of course, I think I had some requests to put some of these Salome files and FreeCAD files online. So while it's calculating, I will just let me go and make it for you. I can't answer every request, okay? But I guess this is a fair request to ask and not too time consuming. So let's copy the one pipe heat exchanger Salome into experimental one pipe heat exchanger Salome. I'll call this define mesh and tetrahedral. Okay, so and now of course I will make a directory for Salome FreeCAD. Okay, so I'll put the stuff here. Okay, let's see. So let me put a lot of that into the files there. I hope this is not too big. If it's not too big, if it's too big, then well, this is about 700,000 elements. Okay, so about 600,000 elements. Just like what we were talking about before. And this is the whole thing. Okay, very big. A lot of meshing to do. Okay, because there are 3 regions there. So it's like running 3 cases concurrently. Okay, we can of course have I'm going to make a new tab here because Linux Mint allows you to do that, and the Cinnamon desktop is very nice. Okay, so let's go and find our Salome. Let's see, FreeCAD or Salome work directory. Okay, I'll save this. I'll save this file here. I'll close, and I won't close it. What's this file? It's a video tutorial one pipe heat exchanger. Wait, let's see, FreeCAD STLs. Video tutorial one pipe heat exchanger. Let's see how big this file is. 25 megabytes. Okay, not too big, not too big. Okay, let's put it here. Then I'll that's the Salome one, and this is the FreeCAD one. This is about 55 kilobytes, not too big, and I will just put it here. Oopsie, I'll put it here. Yeah, go sort it out yourself. This is the one pipe heat exchanger, not too big. So this all should be on GitHub pretty soon. Okay, I'm going to do a debugging star to see how big this thing is. Okay, so I guess, okay, experimental poly one pipe heat exchanger, that's way too big because there are actually ran some files there, but shouldn't be too big otherwise. debugging star git status. Okay, let me just add and commit. Find mesh tet file for one pipe heat exchanger created, and git push. Ah, shoots. Okay, I forgot to add git commit. Okay, there you go. Enter username and password, and all of this. Great. Let me do that again. Right, so you go online and look. All the files should be there. And now I want to export this mesh into the new file. Hopefully it will start to run. Okay, no guarantees that it will be stable. That's the nature of CFD. You have to kind of experiment around until you find something that is stable, a mesh that's stable. So I'm going to replace this mesh in the Salome find tab file. It's going to be pretty big. Okay, it's going to be pretty big. So that's the warning for you. Okay, you don't really have a choice there. So it's going to export the mesh. Okay, and it will take a while. And it could be in the hundreds of MBs, which is not ideal. Okay, it's not ideal, but that's some sort of what you have to deal with. CD experimental one pipe. Okay, heat exchanger, so don't find that. All clean. Okay, debugging star. Oh, great. You see, this thing is actually about 110 megabytes. So this particular one I will not upload because it's way too big. The file size is way too big. It will not fit GitHub's. It will not work with GitHub. So I have the file for you. At least here, you can generate your own mesh, and you can export your own UNV files into your own Git directory. Again, my GitHub's files are inside the description. You can go and take a look there. Okay, so debugging star. Okay, so it's about 110 megabytes. It's huge. Okay, so that's not ideal, but for now, let's do ideas UMV to foam, or let's do an all run serial pre. So that's a lot of cells there. A little too many for my comfort, honestly, but we'll just have to make do with what we have, and let's see whether this thing is stable. So you can take a look here. It's adding cell zones. The copper cell zone has about 200,000 cells. The copper cell has about 100,000, and the tube shell side also about 200,000. So let me run CHD multi-region foam, and let's see how long it goes. So okay, this isn't all that slow. Okay, the hope is of course that it will become more stable, but looks like again we still have an issue here. So looks like the problem's not solved, but well, more instability I guess in the next time, cause it has always been an issue. So we'll need to do some debugging in order to get this case up and running off the ground. So thanks for watching. I'll see you guys again. Bye bye.